It was the last thing you could draw, and I like ran to Jane's office, and I was like, on everything on this earth right now. You should have signed this. Okay. Yeah. Well, see, it was like I'll just stick at it, and maybe it was like kind of over 13 or whatever, and you were the solution manual. And I was like, nope. I got an email. It was like, last thing in the draw. Like, I cut out of the library so fast.
So quiz today, that's part of the period, just like worksheets, except it's not a worksheet, worth more. But no, it's open to open notes, but no conversations. So we may at one point ask you to spread out. And you have to break.
So I uploaded a MATLAB demo for you to try how to draw the PMF and CDF. And you can change the function to draw any model we learned before. This is typically change the T, change the Q, and then you can change the X, the text, the length. I just draw like 20 or 100 and I put some several figures online. You can look at that, or you can just run by yourself and change the number, see how it runs. Starts record. Okay. So we learned the PMF, probability mass function. So basically, you can write like this, and x, the little x, takes on any value, leads to the possible x value, the value of your random variable, and then the probability here. Otherwise, 0. This 0 is not a number of your random variable. This is the probability. So basically, you list all the possible values x can take here, and you add a 0 here to show if you still remember those parts. Okay? So this is not the probability. I saw you make such mistake. Or we learn several models, then, for example, the binomial or geometric, those different model, probability model. This is also a PMF, probability mass function, because you substitute any value of small, the little x. You will generate a probability. So it means the same thing. Okay, so when you are asked to write the probability mass function, you should be able to understand you need to have a general form like this, or you need to be able to list all the possible value for x and the probability for that. Okay, so you basically cover all the possible values of x, your random variable. So we will talk function of a random variable, and basically that's just the derived random variable from a random variable. And then we talk about the expected value of that the derived random variable, and we will talk variance. So we learned expected value last lecture, and we will learn the variance and do several examples today, and talk a little bit about the conditional expected value for the conditional random variable. So first, x is a random variable. If you still remember, when we first talked about the definition of a discrete random variable, I said if I flip several coins or 2 coins, and I can have possible outcome like this. Of course, I know I have only 2 coins, so my maximum head number is 2. And if I care the number of heads I get, so my random variable x can take on value 2, 0, 1. Those are all 1, right? But if I want to know the value, the number of heads, tails I have, of course I know I have only 2 coins. That means 2 minus x is the tail number I can get, right? So this is a derived random variable from x, right? So 2 minus x is a function of the random variable x, and this is also a derived random variable. Usually we use y to represent that. Another example, we buy the lottery tickets, and your x is the how many tickets you buy. It can be 0, 1, 2, countable, right? And for each ticket, you can spend, for example, $2. That means y is 2 times x, right? And I call this function g of x. Then your value of y can be 1, 0, 2, 4, dot, dot, right? So here y is the derived random variable, and it is derived from random variable x, right? Suppose x is a random variable, then gx is a function. So you know, you first have a random variable x, and you know the function or the relationship between these two, then y equals to gx is a random variable. Gx equals 2 times x. This is pretty straightforward. Each x value can generate another y value, right? So if I have something like this, my random variable can take on value -1, 0, +1, -2. What is this? Means y can only take on value.
I thought it was 2 times x. Yeah.
This is straightforward.
Right.
How about we make it like this? Sorry. 2 times absolute value. So if my x can take on -2, -1, 0, 1, 2,
Four, 2, 0, 2, 4.
means actually your y can only take on value y equals 0, y equals 2, y equals 4, right? Otherwise, right? If you know the probability mass function, if I write it just listed in the table, for example, they're equally likely. For y equals to 0, what's the probability? 2, right? So from PMF probability mass function of x can generate probability mass function of y, right? Actually, we know we do like those, but if you just write it out, each value of this little y, if I call it yk, it is generated by certain value of x, right? And it can be multiple. First, negative and positive 1, both of them give me 2 for y, right? So if I want to write out the probability mass function of y directly from the probability mass function of x, what I can do here this small x needs to satisfy y of small x equals y, right? For any value of y, for example 2, I need to find all the little x, positive 1, -1, give me those 2, right? And I sum up those probability of x, correct? Is it clear?
But those are only a probability of 1/5. The probabilities of each little x is only going to have 1/5, right?
Yep. Probability of little x give you 1/5, but that's one sample x. For each value y, little y, for each little y, you find all the possible x. Can be one, can be many, right? -2, -1, 0. If you write like this, for little y take on value 2, is it correct? Because positive and negative x, 1 is the little x which satisfy this, right? Right? So if you write like this, you just find all the little x which can generate your little y and sum up. That's a way to find the probability mass function of your derived random variable, right? We learned the expected value of a random variable, if you still remember. Times little x, right? So each probability of certain value, your random variable, times the value of your random variable, and sum up all the possible value possibilities. That's your expected value for x. So say the direct way to find the expected value of your derived random variable y should be, if you know your probability mass function, that means you know for each little y, each value of your y, you know the probability, and then times the value of y here, right? That will generate the expected value of your derived random variable. So still that example. One way to do this, first way, from the definition, you need first to find the probability mass function of y. And then have another way. So first do the example. Because I know my probability mass function for y. By definition, we can calculate together as I'll leave for you. What's the value?
12 bits.
This? Okay, so if you don't know this, or somehow you just don't want to calculate this out, you don't want to list each possible value of y and the probability for that from this information. If you know the probability mass function of your original random variable x, and you know the function, mapping function from x to y, gx, then we can still calculate the expected value of y. Remember, this thing is sum up all the possible value of little x which satisfy this. right? We just talked this. And this little y equals j of x, right? So for this particular example, for 2, j of x is 4, 2, right? Just for each probability of little x, then I use the value of j of x times probability of this sample plus 0 times these two are same actually, right? Of course, you can write those two together. You first, that is here, right? And this thing is this part, right? So from probability mass function of x, and if you know the mapping function j over x, then you can calculate the expected value of your derived random variable without finding the probability mass function of your derived random variable, right? Should be straightforward.
So she's saying that you can compute the expectation of two absolute value x. That's what she just did. You can compute the expectation of any function x by following that.
Right?
Right?
But
Show how to maybe like absolute expectation of x cubed plus
x cubed,
x squared plus x.
both. So for example, we still have the same x. Basic to right. Px, right? J of x equals, this is 4 plus minus 2, right? Minus 2 squared plus minus 2, right? And for this one is 1 plus 1, 2. This one is 0. This one is 2.
No, that one, the second one's 0.
Oh, sorry. This is 2, 2, and this is 6. Yep. So if I want to call this derived random variable, this is actually u, right? How can I do that? Each jx value and the probability of x, your sample x, right? So 2 times probability, let's see, 0, 0. Anyway, it will be 0, right? Oh, I left the 2 here, but you can list one by one. Right. So you first find the value of j of x. according to each x, you find the probability according to each little x, and list them up. Sum up those will be expected value of this function, right?
I have a question.
Mm.
So when we do the expected value, what exactly then are we, what's our answer?
Where's the answer?
What's the interpretation of that number?
Oh, so you know if I flip two coins, flip one coin to, just flip one coin, I can get head, if I call that head number 0, and I can get tail. Remember, those is a random variable, right? So those are equally likely. Most of the cases in your real life are equally likely, right? So if I ask you what's the mean value or what's the average value of those output, you would definitely tell me what's the value.
1/2.
Yep, you know that. So of course you have this much probability to get 0, this much probability to get 1. Then the mean value in statistics is related to the expected value here. It's like without doing the experiment, what do you expect, right? You have a rough estimation about that. So for this particular case, it's the probability of getting 0 times 0. The probability of getting 1 times 1, right?
Yeah.
So you know mean, you know average, but usually those are related to equally likely. Then you don't care the probability, that part. But actually your random variable can have all kinds of probability, right, for each value. So you need to just change.
So it's like a weighted average.
It's, okay, what it is a probabilistic average. Now this is, I actually disagree with you. In life, things are not always equally likely. In most cases, they're not. You make choices, one's better than another, or you have many choices, right? It's very rare that things are equally likely.
The simplest example would be equally likely. But
right,
in real life, it's much more complex.
Probabilistic model. That's what a PMF is. And in life now, your life, what can happen is -2, -1, 0, 1, or 2. And now this is an example they're equally likely. What would you expect if you were working from this data set, -2 to 2, and you randomly selected a number according to this probability? Now that would mean equally likely. And you calculated x squared plus x with the thing you grabbed out of the cookie jar. What you should expect if you repeat this over and over and over is you should expect, what's the answer to this question? 2 fifths plus 2 fifths plus 6 fifths. 2. You would expect x squared plus x to be 2. Doesn't mean that when you grab the x and you calculate it, x squared plus x will equal 2. But if you repeat this over and over on average, that's what you'd expect. Just like on average in the heads and tails problem, on average you expect equally likely, right? Half heads, half tails. But if you actually flip the coin, you never get 1/2, right? You get either 0 or 1. Now you're doing this not just for what you expect the cookie jar to be, the x, but what x squared plus x is. You can evaluate any function what you likely would think it would be under the probabilistic model. Tangent of x. What would tangent of x be? What do you expect tangent of x to be? That's e of tan x. What would it be? It would be tan of -2 times 1/5 plus tan of -1 times 1/5 plus tan of 0 times 1/5 plus tan 1 times 1/5 plus tan 2 times 1/5. And that answer, whatever that number is, again, is the same problem. You did this experiment over and over, you grab a cookie out of the cookie jar, and you evaluate the tangent of that. You expect it to be close to this number if you did this many, many times. It's very meaningful, and it's an important idea. That's, remember when we said, why do we look at random variables? Because you can now go back and look at how far are you from what you should expect to be. Okay.
And we learned so many types probability model, right? And like the Poisson, and like Dr. King told us, it's related to a arrival event, like within certain time interval, with the probability of that is like a Poisson model, Poisson probability model, right? So with that kind of probability model, then you can calculate expected value without doing the experiment. If you know that's a Poisson or it's a binomial experiment, then you know the expected value, right?
And one last thing is that Feng showed you two ways. First, she talked about if I had a function, and I have a PMF of x, I can create the PMF of y. And of course, it takes time. These are small examples, but even if it's finite, it will take time. And then she showed you how to calculate the E of y in that example, right? Which is the same as E of x formula. It's nothing new. But in practice, if you just need to calculate expectation of a function, you don't need the PMF of y. She just showed you how to do E of x squared plus x, right? We don't need to go and get the PMF every time we need an expectation. Because you're going to find we will take expectations of other functions. And by the way, E of x is the expectation of the function x. What do you expect x to be? And that's exactly what the way we're interpreting it.
But does it like also bridge between discrete and continuous? Because the E function is a discrete data set, and also mathematically shown
E function's not a discrete data set.
But it gives you a number that's not in the discrete.
Just Dr. last time, Dr. King told us.
In any case, it could be.
Yeah, it's an expected value. It's like a standard or a limitation. You're expecting to get there, but it can be a not real sample value. So it can be fraction, of course.
But even in continuous, it could be outside.
Yeah. Yeah.
So, but the expectation exists. As long as you have a probabilistic model, you can take expectations. And that doesn't matter if it's continuous or discrete.
Like a flip a coin, your expectation is 0.5. Is it head or tail? You can never explain. It's not head, it's not tail, right? Because it represents because you're equally likely to get 0 and 1, right?
I have another question. Sorry. When we were doing those, we said that each one was 1/5, so that they were equally likely. That's not in all cases, or is it?
It's not. It's definitely
Why
not.
don't you show them one more example of
Yep.
x squared plus x where you put out it like this, so it just, we shouldn't get tied to that equally likely. It's just a set of.
Okay. Yeah.
Is that clear? 1, 1, 2, 0. 1, 1, 2.
No, you got it wrong again.
Ah.
The first one, 0.
Sorry about that. Okay. So, what's expected value of those? 0 times A. Maybe it's not good.
So 0 times 1/2 and 0 times 1/4 plus 2 times 1/4.
This value. You can have all kinds of probability for the simple x, right? Okay. So we just talked expected value of derived random variable. And remember, actually, we use mu x sometimes to represent those. And this is a constant value. First, when you calculate those out, and the expected value, expectation, it should be a constant value, right? So you can use mu x or mu y to represent that. Then we'll try to find some special case of expected value.
So what does this mean? So this has a meaning in life. No, it does have a meaning in life. What would you expect the cookie from the cookie jar to be how far from the mean, the average? That's what she's doing, E of x minus mu x. So if I grab a cookie from the cookie jar, how far would I expect it to be from the average? Because that's what mu x means, a holistic average. That's statistical. Anyone want to make a guess? What does an average mean? Before we do calculations, so this is like not theory. Let's make a conjecture. What? Theory? No, you're making it a name. So
anything else on divide?
If E value is a number, right? Right? We're going to get a number back.
Yep. First,
Yeah.
let's think those.
What we know mu of x is mu of x is what the average value you expect to get in the cookie jar where you grab one. Okay? Now what x minus mu x means, mu x is already a number. Okay? It's not random anymore. So x minus mu x means if I put my hand in the cookie jar and I look at that x and I say, how far do you think that's from the average? How far do you think it will be? What is an average?
The
You
average
expect x to be the average. In general, if you pick something, you expect it to be close to the average.
Yeah.
So what you'll find and will prove or whatever, convince you, is that E of x minus mu x will be 0. Because you expect x to be close to the average. That's what we expect. Okay. So first thing, you continue now.
So you're expecting the difference between any sample or the sample to the average value. And important thing you need to know, expected value of a fixed number or expected value of a constant number should be just that number. No matter how you expect, it is always the same value, right? So this is the function of x. It's like x minus a number, right? So expected value of this remember, this is a constant number, so I can move it here, right? Interesting part is you sum up all the possibility of the value, each value of x. This will be only this part.
I think she's asking a question.
Yes.
What do you set the sum of the probabilities to be? All the probabilities. One.
Okay, you know that. Why don't answer me? And what's this? It looks so familiar. Yeah. That's the expectation of x. So cancel everything. Expected value of x, random variable, minus the expected value of this random variable is 0, right?
Just a couple of things. One, she wrote E of 5 is 5. Do we understand why?
Here's the probability of getting this 1, so it's 5 times 1.
Yep, great.
Exactly. It's not random. What would you expect the 5 to be? It's 5. The only thing that would be changing, or in E of x, if x is random, then you have to follow the formula. But E of constant is that constant. It's not changing, right? E of mu x is mu x because it's constant. Depending on the problem, you can calculate it, and it would be calculated. Okay?
We're always using those all the time. So
And you want to pick up better, like when you recognize, oh, I'm taking e of a constant, right? There's no derivation need to be done here. And you'll see some formulas I think you'll need to show them. I think just show them and not go into the detail of they can read it.
Another special case is ax plus b, but we just did is x minus a constant number. No matter it's mu x or anything, right? This x minus a number is the example we just did. So a little bit hard to guess. And let's do it. We still treat those ax plus b as a function of x, gx, right? So, and you know this part you will like it because it's a constant number times ax plus constant number. And you know this is b because this sum up to 1. A is a scalar constant number, so you can move it out. And thus, again, is expectation of x, right? So the expectation of your linear function of x, this is a linear function, is the linear function, exactly same linear function of the expectation, right? Should do some example.
So we call this a linear operator. E of x is a linear operator. You know many linear operators in your mathematics. Differentiation is a linear operator. Integration.
We'll look at some example, but think about that. Actually, this E, when you do the expectation, this is a linear operator too, right? Because it's certain probability, quite little p, p1, x1 plus p2, x2 plus, right? Here's the example. So you know the probability mass function of x. What's the expected value of 4x plus 7? You can quickly generate this by looking at this, right? What's the value? That would be so
You have to do plus 0, plus 7.
Someone said 11. Why? Because this is ax plus b, linear.
We can't see it.
Sorry. Expectation of a linear function of x is the linear function that exactly same linear function of the expected value, right? So this is 1, then this is 11. You can do this way. If you know E of x, then you know E of a linear function of x. Or you can do it by the definition. You first list the probability mass function of gx as a function, right? So x equals 0, then you generate 4 plus 7. 1, you generate 4 plus 0 plus 7, 1 plus 7. 2 is 8 plus 7, right? So it lists all the value of v and use the probability mass function of v and calculate the E of v, right? Which is exactly same here. And we'll also come to 11. So that's this page. Variance. Now we come to another important definition. Still think about some example. If I have several x, 1, the value are like those. 3, 1, 3. Sorry, I will make an easy example. If they are equally likely, 1, 2, 3, 4, 5, 6. Worse. It's easy to see it just from all those numbers, right?
I don't understand your grid. You can't have 3 for a possibility.
Oh, I said if they're equally likely, you have several samples, but they're like small value, big value, small value, big value, like those. And you can calculate the expected value. It can, for example, this one is 2, this is.
Oh, you're talking about some function, y equals g of x.
No, x is 1 here, x1. This is the first value of x. So you have probability for this 1/2. You have probability of this 1/2. But you can also have a sample space like this. The expected value is same, 2, right? So if I only know the expected value, I don't know the variance between those, right? I don't know the variance of this sample space. They are very different from each other, right? So still like in statistics, like your teacher posts the grade of your exam, they first tell you the mean value, and it tell you the standard deviation, right? Which means how the sample values varies, right? How they change, it changes greatly or it's very smooth. So that is similar definition is variance. So what you really care is your sample value, how much is your sample value different from the expected value, or in statistics, it's the mean value, right? You have a big, low, high, low, high, low, high, low, or it's very smooth, almost the same. But those can be positive, can be negative. So someone invented this definition. If I put a square here, it would be somehow like an abstract value, absolute value, right? It doesn't have positive and negative. It just represent the length or the distance. So each sample, how different it is from the expected value. And then I do this expected value of this. That is my variance of x. First, you have square here. In order to have the same union, this is called standard deviation. If I do square root, and sigma x is used to represent that. So we'll see some example. Or maybe you can look at one application of that. So now you care how much you're different from the expected value. If this value is very big, that means your sample space have very big variance. That they're very different with each other. Some are very low, some are very high, right? If this is very small, means it's a very smooth sample space, right? And usually, this standard deviation is used very popularly used. We treat this mu x expected value as the center line. Think about this. So the center line of your sample value, the expected value. So within one time standard deviation, if it's this much high, values located here is considered as a typical value. Question?
You're not saying that mu of x is the expected value, are you?
Yes, it is. If we use mu x, mostly it is the expected value.
mu is always
Always.
E of x. E of y is E of y. Mu is E of z.
I just showed you, right? So one-time standard deviation is typical values located here. Any value outside of those is considered as unusual. Okay?
That's a rule of thumb. What a rule of thumb means in practice. You typically expect things to be within one standard deviation of the mean. But that's not as scientific. You'll see later when it's connected to the simple limit theorem.
And very popular in Gaussian. So when you learn the Gaussian distribution, then you will see the standard deviation. It's very important.
In the variance formula, with e bracket x minus mu of x squared, where's the x come from?
Which page, sorry?
The definition of variance.
Okay, here.
The x minus mu of x squared, where did the x
right
come
above
from?
there. X is the random variable.
So we always give it.
It's a random variables. So you have. So again, what does this mean? Expectation means on average. So let's play the game again. We have some cookie jar containing the values the random variable can take on. Inside the cookie jar, some things are more likely than others. E of x minus mu x squared, what does that mean? If I grab a cookie, subtract it from the expected average, and square it. So what would I expect that number to be?
You expect it to be 0.
No.
So you assume that the x is always not expected value.
No. Then can you write the formula, the theorem you just proved earlier down? Yes, exactly. No, the theorem you proved, E of x minus mu x to the first power is 0. E of x minus mu x squared is much different. Maybe do a small example using the definition of variance to show them why one will be 0, expect to be 0, and the other is not.
Oh, okay.
That they're confused. They think they can just square that in the formula and you get 0 squared. That's not right.
How about, so we need to understand.
But why don't you just do that one example that was not uniform? I think you had like a 1/2, 1/4, 1/4 example. Like, yeah, that one.
So you want to verify this, right?
Okay.
We know E of x is 1. E of x minus mu x. Mu x is what? 1. Okay. What's that? E of x, linear combination, right? Constant value, still constant. 1, which is 0, right? So how about expectation of this? X minus 1 square, expectation of this. You can write it out if you want. It will be something like this, right? But you still don't know this thing. So if I list all the possible value x minus 1 square here using 0, 1, 2, it will be 1, 0, 1, right? Correct? This has this much probability. This is P of y, and y equals x plus minus 1 squared. Right?
Okay, everybody see why she got 101? Look at the example 3.32. First one, 0 minus 1 squared is 1. Okay?
So now we can calculate the expected value of this. Of course, we know the probability mass function, and we know all the value, right? So for this 1/4 times 1 plus 0, this 0 is 1/2 times 0. This 1 is 1/4 times 1. Remember, expected value of x minus constant value. If this is just the expected value of x, it has to be 1 here, has to be 0 here. And this is expected value of x minus mu x. Absolutely, it won't be the same, because this is not linear function. You cannot.
Stop one thing. This is variance. This is how it says measure how varied you are. If this cannot be negative, Why? Because you're saying, what do you expect the square to be? It can be non-negative. It could be 0. For this to be 0, now let's think about it. You could do this for any problem, but think about it for any problem. What do you have here? Probabilities. They're non-negative. They're positive probabilities. The only way this could be 0 is if all these were 0. All of them would have to be 0. Now, if all of them are 0, that means what? There's no randomness. Because that means that all of those examples were the same because you subtracted 1 from them. They all had to be 1. So the variance, if it's random, cannot be 0, ever. It could be small, which means you're very close to the average. Probabilistically, you can have outliers, things that are far from the average, but they're very unlikely to happen. That can happen. That could still have a small variance.
Just as Dr. King said, if you really want your variance, which is expected value of x minus mu x squared, to be 0, then your x has to be mu x, right? Your each x is equal to the expected value. It's a constant, right? Absolutely, for a constant value, there's no variance, so variance is 0, right? So we need always remember e of x, if I take square, will never, it can happen to be, but it's not necessary.
Rare. Really.
Huh?
Okay. The only time it happens is if there's no randomness. Can't happen.
Not equal. Okay, then we need to derive another very useful formula. From the definition, you can calculate the variance of a random variable. And what we know is this. If I write out this scalar expected value of the scalar still same, right? Then you notice e of x is just a mu x, so this will become 2 times mu x squared. So variance of random variable equals to the expected value of its square minus square of the expected value. So now you know you even don't need to calculate this sometimes. If you know this, first e of x. And if it's much easier to calculate e of x squared, with e of x and e of x squared, you can generate the variance of x, right? So we can do some example.
Why don't you do the one you just did a different way? 3.32, I think it is.
This one.
Yes.
You already know this e of x, the expected value of x is 1. We just did that, right? And if I want to know the variance, by definition it looks like this. I need to calculate for each x value minus the expected value, 1. So, and then do square, right? And then times the probability for each one, right? So like this, you need to 0 minus 1, 1 minus 1, 2 minus 1, each one square, and probability times that, and then sum up. And I don't want to do the square of a fraction, right? So you know, I already know e of x. Only thing I need to know is expected value of x squared, right? Because x can take on value 0, 1, 2. This is x. So accordingly, x squared should be, and it's all integer, right? So it looks much better. For those, we have a probability 1/4. This is 1/2. This is 1/4. And you know each probability of x squared. So the expected value of x squared is much easier, right? That will be 1/4 times 0 plus 1/2 times 1 plus 1/4 times 4. One. Is it right?
Yeah.
1.5 is my expected value of this, and I know this is just a 1. So the variance of x, 1.5 minus 1 squared, right? We can do more examples, I think, just to practice. 3, 10, 115. So it's page 115. You know all the probability for different d. Big D is your random variable. Then if I want to know the variance of d, which is this, expectation of d squared minus expectation of d, square of that, right? So first, let's look at expectation of d. Each probability times the value one, right? Then expectation of d squared. How about I mark the d squared here? 1, 4, 9, 16. It will be times 1, same probability, 4 times 9. Let's see. 6.1. Maybe my calculation not correct. Maybe. So this value minus square of your expectation is your answer, right? Clear? Another example to be familiar with this. A reference table. what's the variance of random variable big N? Same way. You first calculate the expected value of N, which is 0 times, 1 times, 2 times, right? Square, but I marked the N square here, 0, 1, 4. So it will be 0 times this plus 1 times this plus 4 times this, right? So the variance will be this minus square of this, right? And maybe we can't finish. I will
Maybe take a break. Just one last comment before we break. So remember we made an argument that the variance can't be 0, right? So we now we know the definition of variance, and then we found that a way to calculate the variance, can you write that formula in front of them so they can see it?
no.
No, the way we usually calculate it. That's the definition. The way we typically calculate it, e of x squared minus e of x squared. That's it. Okay? Now, since that can't be 0, what does that tell you? E of x squared never equals e of x squared. That is what she's underlined, never equals 0 if there's any randomness. Any randomness. So that means that never equals 0 if there's randomness. So that's a big error. So you're responsible for not making big errors. So don't ever apply that. E is a linear operator, but it doesn't smoothly go through quadratic. In fact, it's definitely not applied. You can't take the square of your e of x and get e of x squared. It's a big error. Okay. It's great. You do understand, I don't want
Last example you did.
I can give all this to you if you want. That's right. I think we
Oh yeah, that one.
The variable says is always positive, and we can always take more cookies in our hand and less cookies in our hand. Variance is negative. So that means there's no change if we cannot pay one.
You wouldn't expect all the cookies to be the same. That's about variance. All the cookies are the same. You could have statistically, from the point, other times it's wrong. Yeah. But in fact, we expect some variance. Yeah, the variance that we see in practice, actually physically doing it, you would expect it to be close to the probabilistic variance. The probabilistic is not actually physically doing it and getting a sample. Now you're in the world.
And our quiz is again.
Did I? Oh, okay. I didn't read all the questions. Expectation of other budgets. Probabilities, calculating PMS. Put it in our 25.
5 questions.
I think you could do them all in 30 seconds. That's my expectation. I want 25 minutes, so you might have to shorten your conditional.
Yeah, I was just go through that part.
We can do more examples. Where are we?
Oh,
You got to do. You have to do second moments. You just mention these, I think.
yeah.
And then you're gonna do. Oh, you got to do these. Maybe let's go through these, and then maybe we'll come back to this on another day. Conditional. If you don't have much
Or I
time.
can put this online. I have several. I just pick 3.
I would derive them, or maybe derive one and then let them derive.
Okay.
Maybe derive. Find which is the easiest. Well, really easy that. Maybe by no means. Maybe just spend a little bit of time. We'll do more examples. Introduce the problem. And maybe.
Oh, take the easiest and then do example for here and then start.
Yeah, we'll do more arguments. So I can at least start. Creative worksheets from last time.
Yeah, I agree. It's there. How about you and yours?
Yeah, we'll say he drops right off. Yep. I know what you mean. Well, what's the
Another important formula for you. Variance of AX plus B. So we just said the expected value of AX plus B. Linear combination, expected value of linear combination is the linear combination of that expected value, right? So E of AX plus B is A times EX plus B, right? So how about variance? Remember we have, if I just treat AX plus B as a function of X, call it GX, E of variance of GX equals to expected value of GX squared, AX plus B squared, minus the square of the expectation, which is E of AX plus B, and put square outside, right? So what's this part? A square X squared, B squared, and this is a constant, and AB are scalar. So I'm write it like this. There will be a square e of, see, this is linear, right? Linear part. So I can move it, move the expectation. You will always use that. The expectation of linear combination is always linear combination of expectation. Okay, so 2ab scalar e of x, e of this constant, always that constant, right? Minus the square of this whole thing is square plus 2ab mu x plus b squared. So let's write it as e of x squared plus ex is mu x, 2ab mu x plus b squared minus a squared mu x squared minus 2ab mu x minus b squared. It looks very nice. This cancel. This cancel. Only part left will be a squared e of x squared, a squared e of x squared outside. Okay? So that will be a squared minus right? Or you can write it like this. Mu x squared. This is the variance of a linear combination. E of x squared minus square of ex is your variance of x. So that tell you variance of linear combination is not combination of linear combination of variance. It actually doesn't care the constant, because constant doesn't generate any variance, right? Constant is always same value. The constant doesn't generate any variance. Only thing matters is this ax, and you need to remember is a square. Okay? If you cannot remember it, I suggest you derive it by yourself after class. Okay? And we saw a lot of e of x squared and ex. Actually, e of x, the nth power is called the nth moment of x. For some reason, it have such name. So it would be easy to remember the variance of x this formula again. This power of 2, second power, so this is the second moment of x. And this is the square of the first moment. Right? So variance of x is the second moment minus the square of the first moment. So this is called nth moment. And the variance is also expectation of x minus mu x to the nth power is called the central moment, nth central moment. So if it's It's the second moment of x, second central moment of x. Why it is called central moment? Because we are somehow viewing this expected value as a central point, right? So this is called nth central moment, and the variance of x is the second central moment of random variable x, and it is also the third moment, sorry, the second moment of x minus the square of the first moment, right? Because this is the nth moment of x, this is the nth central moment of x, okay? We learned several probability models for discrete random variable. And you need to remember this, or if you cannot remember this variance, last time we learned all the expected value in the page 400. If you cannot remember those formula, you better like read it, crib sheet during exam, and you will also need to look back when you're dealing with probability, all kinds of probability model, because it's benefit to know their expected value and the variance. So last time we read all the expected value here. So I will pick one. We know the Bernoulli expected value of this is pretty straightforward, because they can only take on value 1 or 0. I made a mistake here. So expected value is p, and if you calculate the variance, it will just be probability of being 0 and probability of being 1. This is the expected value, remember, so it's probability of being 0 times 0 minus mu x squared. We are calculating the variance of x, right? Plus, because we have only two cases, probability of being 1 minus mu x squared, right? And thus is p. So that's why it's 1 minus p times p squared plus p, and 1 minus p squared times p here, right? And we'll give you p minus p squared as the variance of a Bernoulli random variable. For the binomial random variable, the easy way to do that is to first calculate e of x squared, calculate e of x, and we know e of x is NP is easy to remember. Actually, you need to use this formula to derive this to be NP. I will scan this to upload. How about you can derive by yourself after class, and if you have questions, then you can ask me. So you just substitute into the probability of each sample if that sample takes value of k, and then you will need sum up all the possible sample value and times the probability of that, each k times the probability of that, and then this k from 1 to n, I can cancel this k with this k factorial. So this will be k minus 1 factorial. And then I move out 1n here. Then the upper part will be n minus 1 factorial. And I use I equals k minus 1 to generate this form. And this is actually p plus q to a power. If it's hard to understand, then this is a form of this. Okay, so p plus q is nicely always 1. So it will
basically that's the binomial theorem that you should see in like a pre-calculus class. A plus b to the n.
So that's n times p. And the same way, you can do this, will give you n times p, and p plus q. This q can also write as 1 minus p, right? So it will consist with the book. And you need to derive all the other probability models. We will quickly talk about the conditional. So we will learn the probability mass function for the I will have to go here. Oh, it's here. Sorry, then just go back. Before, when we think about the conditional probability, we always talk about events. Like probability of A conditional on B. So B is an event as your condition. If we write the probability mass function, it will look like this, little x. This is big X. Okay. B is your condition. X take on value little x. Probability of this is just this. So the way to write a probability mass function is P big X condition on B. You marked here, right? For example, the coin. We have 2 coins. If I have 1/2 probability to use C1, 1/2 probability to use C2, remember we did this before. Suppose this one is not fired. If my condition is using the first coin, what's the probability getting ahead? Means my little x, if I mark head as 1, tail as 0, little x equals to 1, and my condition B is using C1.
3/8.
3/8. Giving you condition of using C1 means you are already here, right? Yep. You did this before, exactly same. just use different symbol, right? To be general, you need to know how to write the probability math function for conditional probability. Conditional probability is still probability, right? So it's just a general form on that. And another word which will be very similar to you is PX. This is in your slides. You can just read after this. This is using C1, but I have two different cases. I can use the first coin or the second coin, right? So if I ask you what's the probability of getting head x, little x equals to 1, the total probability of this you did this before, much more complex. You did head, right? Now I just have one head, I just flip once, right? So it will be first case use C1, second case use C2, right? If I know I use C1, which means I'm in this part, knowing the condition here, the probability of giving C1 having a head, this is 1 actually, right? This is x, and the little x takes on value 1. This part, same, your little x takes on value 1, but you are using C2, right? So those will be 1/2 here times conditional probability 3/4 times 1/2 here, the other branch, times probability, conditional probability using C2 to get head, right? So that is the total probability to get a head, right? We just do the example again actually, and you did this before. Another example, if I have 10 number 0 to 9, and I call B1, B2, two different conditions. This is, so the experiment is just to pick up a number from this is my sample space. First condition is knowing the number I picked is even. The second condition is knowing the number I picked is odd. What's the probability for example, x take on value 2? Knowing you're in the even subspace of this, right? So your original sample space is 0 to 9, 10 numbers. If you know you pick out an even number, which can only be 0, 2, 4, 1/2. Yeah, because you know you're in B1, right? So you take out this exactly number, just this sample out of this 5, so it's 1/5, right? Same here, you can do more examples. So if for a certain condition, If I sum up all the samples that actually belongs to B1, the probability of, that means I will do 0 plus same condition, second sample, third sample, it will be what? 1. Yes. First, conditional probability is still probability, right? So we will follow the general theorem of probability. If I name C a subset of B, this is even number within the 0 to 9, which is less than 3, for example. So X is CI is even and smaller than 3. You know it can only be 0 or 2, right? So the probability of being in C and knowing it is within B1 if I write it out, it will be, for 0, I will need to find all the value x which satisfy it is in C, and the probability for this, knowing given condition B1, knowing you're in the even set, and to be a 0, what's this, right? Knowing you're in the even set, to be a 2, 1/5, right? So the probability of given condition you are in the even set to be an even number which is less than 3 will be 2/5, right? So this is this theorem. Just find all the sample which is in C and know all the, it's knowing the condition B here and same here. Okay, so like you are already limited to those sample space. Then anything you do is within the sample space. You just sum up part of the probabilities. If I sum up all the probability within the sample space, conditional probability, it will sum up to 1, right? Because conditional probability is still probability. So. Then the expected value of conditional probability, it just uses as a probability. But remember, you are limited to this condition B, right? And the value of your random variable times this probability sum up exactly same as, not same, just similar with the general form for expected value, right? So expected value of conditional probability, we need to remember this. Then if I have several different cases, like the coin, right? B1, B2, or like even all number B1, B2. This is very similar to the law of total probability, right? Expected value. Then we can try this. Just try this and then stop. So half probability to be C1, half probability to be C2. How about I call B1, B2, and then 0, 1, 0, 1, 0, and this. I want to know E of X, which is first, if I am here, for me I can calculate using condition B1, using the first coin, the expected value of your experiment, your random variable x, is 1 times. Of course, you have to use conditional probability. You are within the subset. You are using B1 as your condition. You know you're here, right? So 0, which is right. If you're located here, you're using the second coin, means you have to use conditional probability, which is make it different. Right, and I want to verify this will be plus times the B1 times probability B2, different condition, right? 1/2, 1/2. So it's 1/4, 3/8. I don't know if my calculation is right. Need to verify. So if I do this just by this, it means getting 1. My probability to get 1 here, exactly that one will be this, right? Times 1 plus getting the 0, 0. Here times 1/2, 1/2, 1 times 1/2, 1/2, 0. Four, 2.
No, the 1/8 is 0.
Oh. So it's same, right?
So this is different than what we did earlier because you're making it conditional.
It is same, just easier, because we flip 3 times in the worksheet. I will just flip 1 time.
Well, I mean, the only difference between the expected value of this and the expected value we did earlier is that this is, we're considering that it's conditional.
Yes. Yeah. So what you're saying is, what this means, because I'm going to talk a little bit about chapter 4 now.
Okay.
What this means here is that if you know B1 happens, what do you expect X to be? Well, look, it's skewed. It's 3/4, 1/4 skewed. And so now you would expect if you're there to be 3/4. And what would you expect X to be if you know you're in B2? Well, again, it's 1/2, 1/2. So you expect it to be 1/2. Now, in general, this is like a little game. It's a 2-part game. What's the game? You flip a coin to pick a coin, 1/2, 1/2. Equally likely you pick the coin, right? And then you flip the coin itself that you got, right? There's 2 coins in here. Don't know which one is. So the first thing I do is I randomly pick a coin, and I flip it. 2 parts. Now, in the end, I flip the coin, and I'm going to get one of 2 things, heads or tails. Heads is a 1, tails is a 0. So rather than thinking of it as a 2-piece game, I can think of it just as an output. The output's heads or tails. That's X. That's X. What do you set X to be? Well, you got to analyze all the probabilities. You've got this tree now, and you can. You should be able to. We were there, chapter 2, right? And you should be able to calculate that the probability of getting a 1, the heads, was, I think it's 5/8. You did calculate it. Not calculating the X, I'm just saying calculate it. The probability of 0 is 3/8. That's using the tree work we did before. Now when you calculate E of X, what is it going to be? It's going to be 1 times 5/8 plus 3/8 times 0, which is 5/8. Now what Thing was talking about is that all these things are connected. That if you have you know about conditions, so you were given this, then you actually can predict what this is without deriving the mass function x. How? you take the expected value of x given b1 and then multiply by the likelihood of b1. And then you take the expected value of b2 and multiply by the likelihood of b2, and that gives you the expected value of x. Now, you got to get a handle on notation, because you can see we're building and building and building notation. And sometimes these things look odd, but this is just an e of x. But this is telling you where you are in the world, what you can assume is true. You know b1 is true. And that's important for you to say, because that means what you expect on average to have changed. Another thing I wanted to talk about, I just want to make it clear, so I'm going to just, and then I'm going to talk a little bit about chapter 4 before you take the quiz. Take the quiz around, what, 8:05 or something like that? 8:05. Without variance, because I want to make sure you got it down. So you get variance of x, and that's this thing here. And we're talking about it in the context of discrete random variables. So we have these values, x1, x2, maybe x3, x4, x1. Sorry. And then they have these likelihoods, right? This is the mass function. Okay, so this is probability. And then you calculated mu x. Mu x is a number. Mu x is, you have x1 and the likelihood of x1 and x2 and the likelihood of x2 and so forth, and then you calculate mu x. And maybe this is mu x. Mu x is a specific number, and we're going to graph it. We're going to place it on, actually this is not it, the x-axis. So here, suppose mu x is this. All right. Now, I got colors today. This distance is the distance between x1 and mu x. This distance, just talking about the values on the number line. This distance is between x2 and mu x. This distance is between x3 and mu x. This distance is between mu x and x4. Well, remember, always doing x minus mu x. So this minus this, this minus this, this minus this minus this, and then the last one is this minus this. All right? Now what happens is when you do x minus mu x and you're over here, you're getting negative numbers. And when you do x minus mu x on this side, you're getting positive numbers. Now if you just add them up, that's really meaningless. What you have to do is multiply by our likelihood, meaning you take this distance and you multiply by the likelihood of this. That's this height, and so forth. And what will happen? That's this. And that's 0. Right? We talked about that thing, derived it in front of you and showed it was 0. Which means that if you wanted to look how varied things are, just subtracting the value from the average and adding them up in a probabilistic manner doesn't give you much insight. It gives you 0. So it's no insight. So if you want to talk about how varied, you see how varied they are? This is this far away, and 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 this is this far away. You don't want to just take the difference. You want to take like a distance. Now, one thing you could have done is this. Absolute value. What do you expect that to be? And that would actually give you good insight into how far they are. The reason why we don't stress that, and the variance isn't defined that, is because actually, and you should know this from your calculus course, is that the absolute value function is a little nasty in terms of derivative. It's got a sharp change, and it's not differentiable there. Quadratics are differentiable, so you get nice properties. So what you're doing then, what variance really means, is you're calculating this distance. Now it's negative, but you squared it, and you multiplied by the probability. You calculate this distance, you squared it, multiplied by the probability. You calculate this distance, square it, multiply probability, etc. That's what this will be. And it gives you a number, a non-negative number. What kind of number is that? It's like the average distance squared. It's a distance squared, remember?
difference is distance on the number line. A minus B is the distance between A and B. But because you squared it, it is getting the square. Now, they call this variance thing. I'm not sure if she wrote that, but that means you usually use sigma, lower Greek letter sigma, squared for variance. And what people will do is take the square root of that, and that's the standard deviation. What's the standard deviation? It is like the average distance, probabilistic distance between random variables and the mean. That's why when Thing was looking at mu x plus, or what was it, x plus mu x and x minus mu x, you expect most of the numbers to lie in sigma x. Yeah, I'm sorry. That's why I wasn't listening, sorry. Mu x plus sigma x. Mu x minus sigma x. You're going around here and you're going up one deviation, standard deviation. You expect everything, not everything, you expect most of them to be there. Okay? So notice that this is sort of a distance squared. It's called sigma squared. It doesn't mean you square the answer. It means it is a square because that's what you calculated. Okay? And it is giving you variability. Like in this case, you're getting certain variability. What would happen if you had your mu x, here's your mu x, and here's your x's. And I'm not even putting the probabilities. They're all in this one band. You expect it to be a very small variance. But you could have one way out here, and still it could have a small variance because the likelihood of this could be really tiny, because again, low probability. All right. So let's recall fxx. This is called, again, the cumulative distribution function. And what it represents is a function of x. And what it represents is the probability that capital X, random variable capital X, is less than or equal to little x. That's what you're evaluating at. Okay. And what we find is the following properties. We found one that fx of minus infinity should be 0, and that means you're taking the limit of this as x goes to minus infinity. Fx plus infinity should be 1. Fx of x should be non-decreasing. That is, never where is it decreasing. It's either horizontal or it is rising. For discrete, what we found, we saw pictures like this. Remember, this is probability here, so you're between 0 and 1. So you may be, you're here, and then here, you're there. And then you're here, and then you're there, and so forth. Now, it could be finite, or it could be countable. It just keeps having these steps. Okay? So that's x1, x2, x3. This is a discontinuous function. This is coming from your calculus that you're so very familiar with, right? You're getting, what do we call these things? We call these jumps. All right? And what a jump means in this context is that the probability that x equals x1 is this height. The probability x equals x2 is this height here, because again, it's this height here because why? Fx of x2 is this, and that would include this one and this one, and that's why this part here is coming from this probability, and this part here is coming from the probability x equals x2. And so these jumps literally are telling you the probability at a given point. So you could have a discontinuous cumulative distribution function, and if it consists of just jumps, what are you seeing? What you have is a discrete random variable, and you have positive probability at that point. And you can actually calculate, if you have this gridded out, you can actually calculate the probability point. Okay? Now, of course, you could have, the next case we're going to consider is what if the cumulative distribution function was a continuous function? So what would that mean? It still would have to satisfy this, because it's still this. To the heart, that's what we're talking about. So it still has to have these properties. It is probability. Fx of x must be between 0 and 1, always. And it should not be decreasing ever. Never be decreasing. So what could it look like? It could look like this. It could look like this. Now it's continuous. So again, when I used to teach calculus and talked about continuity, I'd say, well, the idea of continuity is that you're drawing a graph of a function, so it passes the vertical line test, but you never move your pen off the piece of paper. And so you know that kind of result. Of course, this would have to be 1, right? If it's flat, this is 0, of course. And there's an example of a continuous fx of x. Another example could be something that looks like this. Oh, we're talking about, sorry, that's not right. That can't happen. Can't drop. And you got this 1 here, and it never reaches 1. That's a possibility as well. Okay? In both cases, they satisfy f of plus infinity is 1, f of minus infinity is 0. F of plus infinity means the limit now, not evaluate, and minus infinity and so forth, and it's increasing. So both are examples of continuous cumulative distribution functions. Okay? What do we find? We'll characterize this random variable as a continuous random variable. In this case, this would be important. What are these places? The fact that it's level means you're not gaining any probability after a point. And here, this is not providing any positive probability here. The question is, like, what's this value, x2 and x1? And what you're going to find in this case is that there's something interesting going on about the random variable capital X between the intervals x1 and x2. In this case, there is no starting point. It goes on forever and never reaches 1, and so forth. In this case, it's all possible numbers, random variable x. You've got to examine. Okay, so okay. So we're talking about a continuous curve, and as you know, a lot of this is coming from the heart, is coming from calculus. In this case, because it has these nice properties, this function will be differentiable. I don't know. This function will be differentiable almost everywhere except where? At the sharp points. At the sharp points, it does not have a derivative at x2, and does not have a derivative at x1. But everywhere else, it has a derivative. And what's the derivative here for any x here? We're talking about tangent line, right? It's going to have a horizontal tangent line, derivative 0. Same thing here. Okay? Now, this is a more interesting curve. This is a smooth curve everywhere, so it's looks to be differentiable everywhere. Derivative is never 0. That doesn't appear to have any horizontal tangent lines. This is increasing always and rising, so it's going to have a positive tangent line, but it may be very small, very near 0. Okay? So, in the case of a continuous random variable, so again, what is a continuous random variable? It is a random variable, x, which has a continuous CDF. We can then talk about the derivative. So remember that this is a function of x, so you can take the derivative with respect to there's no two variables here. This is just a name, the random variable, and this is what you're evaluating at. You can then take the derivative with respect to x of this. In the same context as you've done before. Derivative of a constant 0, derivative of x squared is 2x, derivative of x cubed 5x. Derivative of e to the x is e to the x. And of course e to the x is, what's the derivative of e to the negative x squared? E to the negative x squared times negative 2x. Those kinds of properties you're inheriting before. Nothing new. This is some kind of function. Of course, it's related to the random variable. It's a function of x, different function. Y used the same letter f. Historically, in fact, you can actually recall what you learned in calculus when you talked about antiderivative. Remember, integrating f of x gives you this antiderivative, and then I'm almost certain that in your textbook, when they talked about integrating the indefinite integral of little f, and they used little f all over the place, they used capital F. So we're using the same notation in that context. Okay. This has got a special name too. This is called the PDF, not a Adobe PDF, but probability density function. And frankly, what you're doing is you're taking the derivative of this thing, which is this. Probability x is less than or equal to x. Okay? Less than or equal to, remember? So what is this? This is this is the same as the limit as delta x goes to 0. I mean, this is what you should have seen 3 years ago. This stuff. A long time ago. You're not responsible a long time ago. But what is this? Do you remember what the difference between two capital X means? You're thinking more about this, but I'm going back to, remember those properties of this thing? I did write it. Remember, one other property was that fx of b minus fx of a is the probability that x is less than or equal to b but greater than a. Sorry. It's bigger than a, strictly bigger than, and less than or equal to b. Remember? And that assumes b is bigger than a, of course. So same thing's going on here. You're talking about this little probability that you're in this little sliver, the sliver between x plus delta and x. And then you're dividing by how wide a sliver. Remember, this is a probability, and this is not. And you're taking that ratio. And yes, you are getting a 0 over 0 type limit. But the nice thing about it is that all those rules of differentiation we inherit, so we don't have to go and derive anything. And so when you think of, if I have a, this, fxx equals 1 minus e to the negative x, graph that. What does it look like? I think it's, did I make a mistake? I believe that the limit as x goes to infinity of 1 minus e to the negative x will be 1 minus e to the negative infinity, if you allow me to write that down. It's bad math. But that's 0. So you're getting 1 minus 0, which is 1, which means if I go far right, I'm getting 1. What's the limit as x goes to negative infinity? E to the plus infinity? We don't want that, do we? Did I make a mistake?
Negative infinity.
I'm getting too small. I shouldn't have showed you an example. I blew it. I'm sorry. What I wanted to do was show you the derivative of this. So anyway, this one doesn't work. That's what happens when you think of an example off the top of your head. Let's just grab one from the floor. Ignore. Actually, it's probably here for when I wanted to. But I'll cheat and go to an appendix where all the calculations are derived and say, okay, here we go. So we're now away from discrete. Derivative constants are 0. Problem about discrete, now we'll get to, here's the one. So my blue pen, for me to give you fx of x, you have to integrate fx of x. So we're jumping the gun here, I'm sorry. And that's your fx of x. So I was trying to give you it's called the exponential distribution function. So I won't do the derivation. But this is an example of something which has already been differentiated for. This lambda is just some constant. You can choose any different constant. You get different properties for this. And this is an example of what the PDF could be, probability density function. Okay. So I don't have that in front of me. Let's see if they have one nice one done in the text. They're going to start throwing a lot of calculus at you, because once you define derivative, you're going to find is you're going to have this ability to do all kinds of quick derivations. So this is just an introduction to continuous 4.1, sorry, which is good reading material, but not covering, because it's really not very helpful to understanding. It may help motivate you if you feel that. So again, what we did is we started off with the CDF. We recalled these properties, and we just mentioned this property a moment ago. We defined the continuous random variable when the CDF is this. They're not going to do the example based on that, and I'm skipping that because I'm not sure how helpful that will be. And here's a nice one. Here's a nice one. This is the one we were doing a moment ago, for very similar. You're 0 when you're to the left of 0. I don't know why you asked yesterday. They put the axis here. You've got the y-axis actually here. It's not the y-axis. Then it's the straight line x. Y equals x. That's this here. And then after 1 is 1 always. The derivative of this is a very nice function. The derivative of this will be derivative of 0, 0. Derivative of x is 1. Derivative of 1 is 0. So what we would get here would be of course, I remember having students do this, and they'd say, how do you get 3 derivatives? Of course, it's a piecewise defined function, right? Because this function was defined in pieces. The derivative function is defined in pieces. It's 0 when you're to the left of 0. And it's 1 when you're to the right of 1. And it's 1 when you're between 0 and 1. What about at 0? What about at 1?
Undefined.
It's undefined because it's a sharp point. The derivative doesn't exist. Technically, you have a left-hand derivative and a right-hand derivative, and they don't agree, so you say the derivative doesn't exist. Okay? That's your PDF in this case. And if you integrate this, you'll get the cumulative distribution function. Okay? So they're connected this way, just like before. Okay. Yeah.
So the f1 and then 0 smaller than x smaller than 1.
Are we talking about this, this, or this?
The
blue.
The blue? Okay.
Yeah, why don't we have the equal sign?
Because again, this is a derivative. This is a derivative. Really what I want to show you, it's this picture is telling you, because at 1 you're here, and that's a sharp point, change. On the left-hand side, you're getting, the left-hand derivative wants to be 1, and the right-hand derivative wants to be 0, and for a limit to exist, and that's what a derivative is, the left-hand limit must equal the right-hand limit. So therefore, anytime you have a sharp point, the derivative won't exist because the right and the left-hand derivatives won't equal each other. Okay? And the same thing happening here. So technically, that should have been handled in the calculus. But from our point of view, we know that if we integrate this, we get this. And then there's some extra properties, like how do you get, you can clearly see you get x, but 0, when you integrate, or actually the derivative of this is this. You can't integrate 0 and get 1, but there's some properties that tell you this has to be 1. Remember the properties that we talked about? These properties here. Okay? Okay. So let's go here. This is quiz 4.2. So quiz 4.2 is going to ask you a couple of questions, like what's the probability that y is less than or equal to negative 1? What's the probability that, this should be capital Y, of course, that y is between 3 and 2? And what we get in the first case is this is your cumulative distribution function, reminder, review. What does that mean? This is the probability that y is less than or equal to y. So it's a beautiful function to use when you have left-tailed questions. That is, you're allowing the random variable to be any number less than or equal to y, while you simply evaluate at y. So this is a left-tailed problem, left-tailed. So what do? We simply evaluate at negative 1. And we get 0, according to the rule. Right? The next thing is the difference of capital F's is exactly the formula you want to apply here. This is simply fy of 3 minus fy of 2. So fy of 3 is 3/4, and fy of 2 is 2/4, and so we get 1/4. Okay? And so forth. This problem should be straightforward. What about this problem? How would you tackle this problem? Yeah, I mean, remember that capital F is here. The interval being greater than 1.5, greater than means this, is the complement of this. This probability is given by your function. So for you, you simply evaluate at 1.5. Okay? So we'll continue on tomorrow talking more about the density function. What you're going to find in the world of discrete, the PMF is important, really important. And if you know the PMF, you can get the distribution, the CDF. You got to get to know your acronyms. In the world of continuous, and by the way, if you have the CDF, you can get the PMF by what? Taking the difference of the jumps. Remember the picture? Now, in the world of continuous, the density function, the PDF, from the PDF, you'll be able to calculate the CDF. And if, by the way, if you have the CDF, you can get the PDF, don't use M for continuous. So given the distribution function, you can calculate the PDF by taking the derivative. So it really says if you know one, you know the other. If you know one, you know the other. In the world of discrete, what's really good is the PMF. Why? Because you want to do that to do like expected values. You use it all the time. You saw thing apply over. So PMF's a little bit easier to use, or not easier, helpful. And if you have the CDF, you can calculate it, so that's okay. In the world of continuous, the PDF is important. You're going to be integrating, not adding. So you're going to find you're going to do a lot of integration now. And if you have the PDF, that's going to be how you find the expected values in this world. But if you have the CDF, what do? You can take the derivative. Further, you can easily get the CDF from the PDF by integrating, going the other way. Okay, so they're related. Expected values are important. The PDF in the continuous world, the PMF in the discrete world. So now you have a quiz. And again, unfortunately, this is where this is a little bit different. It's going to be probably easier than some of the worksheets, but you work alone. So we expect you to work alone. You can use, you don't need to close your books. You can use your books and your notes and so forth. But we don't want you to. Cheat sheets, it's fine. But not on Excel. All right? Well, my proof sheets are not notes and books. Oh, it makes sense. I don't care what you use. You can't use so, well, that's okay. Now you have the rest of the class, but if you need more time, Thing is probably willing to provide more. You may need to come back to this, so I'll leave this open. I'm going to take off, okay? Okay. So tomorrow, you can do maybe some more examples of this expected value. You can do more examples where they're not likely. They could be small case, and then I will do. So and then you do 4, 6, and if we get to 4, 7. Okay. And then you will do a handout. Maybe chapter 3. Or what you're doing. Okay. And for this, obviously, you can use any calculators you want. For exams, we'll probably limit the kind of calculator you can use, like non-programmable and that kind of thing. You can just set up problems, and you don't have to do all the calculations. However, it must be clear to us that all the values are determined, very clear. Meaning, like if there's a 3 factorial divided by 2 factorial divided by 1 factorial times 1/2 to the 5th. That's suitable, but not px of 3. Okay. But if you have questions, ask them.
Okay, last question. You play 7 games. You know you win the first time. You know you win the second time. You know you win your fourth. I win twice just now, right? You know you win your fourth in exactly the 7th game. Right?
So between 3 and 6, you win again, but it doesn't matter which. Right?
You should think by yourself. So you win the 4th game in exactly 7 total games. When you play the 7th, the last game, you win your 4th. You know you win twice. First time, second time, right? That's all information you know, then you know how to select.
So for the last problem, is it saying that only win 3 games in 7 total games? Or it doesn't matter if you win the 3rd game and the rest 5, 6?
You know you win 4 games, 4 out of 7 totally, right? You know?
So you are winning 4, not 3.
Yeah.
Yeah, of course you are winning the 4th.
Okay.
Of course you are winning the 4th at the 2nd game, at the 7th game. So if there is a 4th there, that means you at least you win 4th, and you just play 7, so you exactly win 4th and exactly play 7 games. Pay attention in problem 1. All the sub-questions are related with the PMF gave you at the very beginning. Okay? So the question C asks you EC and PMF of PC. The X random variable is the still same random variable placed at very beginning. So you can use the PMF for X.
Okay, so that's the one. Okay.
You play 7 games. Only thing you know is you win the first one, you win the second one, you win your so those are the first win, okay? Second win, and you know your fourth win. Is it right?
So this is one probability question. It's not asking
Oh, it's not
one
asking like,
probability and then another.
and then it's asking the probability of those events or this. Okay.
To go over what happened, things have to change. Figure out what this is. Okay.
There's some off-campus students who speak online. wants to calculate exact probability of certain events or certain outcome, it is possible to be not of any of the model you know, but you need to think how to analyze that. It can not just be a model you know. So don't try to apply or try to always apply the model from written. Particular case cannot be. those pictures show the diverse colony. They have to have certain shooting. I think so we don't understand the problem. This image we can use condenses color all on the way. So the PMI for certain technologies, or like technology 4, which is the, and to use the sparkulating to decide per behavior for this city template or city most using fiber and using because I think is really
Choose one.
those are the whole random questions, so those probably should be used here.